Hello, I'll be presenting our paper, Reading Between the Lines, Modeling User Behavior and Cost in AI-Assisted Programming. I am Hussein Mozannar. This is work jointly with Gagan, Bansal, Fourney, and Eric Horvitz at Microsoft. So we'll be talking about GitHub Copilot. So Copilot is a large language model embedded into your code editor. And at each moment of time, when you pause writing code, Copilot will show you an inline suggestion in gray. And this suggestion compromises entire function completions and entire classes, and not just single sentence or word level autocomplete. And the programmer can accept this suggestion by pressing the tab button, or reject it by continuing to write or pressing escape. Copilot is now being used by millions of programmers on a daily basis. And maybe the first burning question is Copilot useful to these programmers? Initial research found that there was no effect from using Copilot on program productivity. But follow-up research from the Copilot team showed that programmers are 55% faster with Copilot. So they ran a randomized control study where some participants had Copilot and the others did not, and found that those that did have Copilot completed tasks twice as fast. And going from these results, we can see that there is some evidence of short-term productivity improvements. And the question now becomes, how can we improve Copilot further? And the approach we're going to try to take today is that we really need to understand how people are using Copilot so that we can diagnose current inefficiencies, and future work can try to remedy these inefficiencies. Now, Copilot is really changing the way we write code and introduces many new activities for programmers, from things like prompt crafting, verifying suggestions, editing suggestions, and so on. And these activities are not captured in telemetry or in other ways, and really require us to take a closer look at how programmers are writing code. So on this slide, I'm showing you on the left a video of me writing code. And on the right, I'm going to track with a state diagram different activities I'm doing as I'm writing the code. So I start off in this purple state, writing new functionality, as I write the function signature of my code. After I write for a little bit, I'm going to pause for a bit so that I can think what are the arguments for my functions. So I transition from writing code to thinking about code. And at this moment, Copilot interrupts me and shows me a suggestion. But I'm not really thinking about that suggestion because I'm trying to think about what I want to write. So I reject it and go back to writing code. After I'm finished writing my function signature, I'm now expecting a suggestion, and Copilot shows me a suggestion, so I'm going to verify it. So I transition to this dark green state verifying suggestion. However, the suggestion does not accomplish what I want at all. So I will reject this suggestion and go to the purple state of prompt crafting. So I'll try to write a prompt of what I want Copilot to do, which is initialize the weight and bytes parameters of the regression model. And after I prompt craft, I will accept the Copilot suggestion and go into this loop where I wait for suggestions, verify them, accept them, and so on. And then comes a moment where I don't like the suggestion. So what I will do is I will go back to prompt crafting. And then Copilot is going to show me a large suggestion, which is the body of this for loop, which I will decide to accept without verifying. So I will defer my verification for later. So I transition to this light blue state on the bottom left, where I accept the suggestion without verifying it. And then afterwards, you can see my cursor verifying that suggestion line by line until I find something I don't like in the suggestion, and so I decide to edit it. So there's lots of observations from just watching this video. For example, all the different activities I'm doing, the times I'm spending doing them, the decisions to accept or reject suggestions or verify them. And to really make these observations more concrete, we designed a taxonomy of these states. So we call this taxonomy the Copilot user programming states. And in essence, at each moment of time in your coding session, we can characterize your behavior during the fragment as one of 12 states. So these are granular, but they're not meant to be comprehensive. And they include typing states like prompt crafting, writing code, editing code, and more thinking states like verifying suggestions, verifying code you want to write, and other things. Really, we can represent a coding session now as a timeline of these states. And the transitions between states are due to Copilot showing suggestions and our actions to accept or reject suggestions. And this data really requires granular annotation. So we performed a data collection study where we had 21 programmers at Microsoft first perform a coding task for 20 minutes. And we record their video of themselves writing code and then align it with telemetry. And then the programmers themselves retrospectively self-label their session at each fragment with the most appropriate cup state. So we created this video labeling tool, and at each fragment of the telemetry, the programmer will click on which cup state is more suitable. Given this data, perhaps one of the most interesting findings is understanding where the programmers spend their time. So on this graph I'm showing you on the left, for each of the 12 cup states, and I'm highlighting in light green those that are Copilot specific interaction states, like verifying, editing suggestions, the percentage of the session that is spent in each of these states. And we can see that the dominant activity is that of verifying suggestions, taking up to 22% of session time. And the second most dominant activities are writing and thinking about code. And if we sum up all of the states that correspond to Copilot interaction, so those are light green, they comprise 50% of session time. So now 50% of your time coding is spent interacting with the model. We took a closer look and found that only 34% of the suggestions were accepted. And so combining that number with the cups information, we can derive that 22% of session time is spent verifying almost 70% of suggestions that get rejected. So that's an upper bound on time that's really going to waste. So 50% of time is spent verifying suggestions that will be rejected. And in follow-up work at AAAI, we show how we can reduce this inefficiency. Another insight we can derive from this data is understanding transitions and patterns of behavior. So on the right, I'm showing you a graph which plots transitions from each state to the other in the data we collected. And really, we can model programmer behavior as a Markov change on these cup states. And there's many transitions that we do anticipate. For example, prompt crafting to verifying suggestions, or waiting for suggestions and then verifying, and etc. We can also look at more longer-term patterns, like n-grams, so 3 consecutive states, 4 consecutive states that most commonly occur. And we can kind of see patterns of behaviors like iterative prompt crafting, where the programmer would write a prompt, check the suggestion, and then tweak their prompt to get a better suggestion, and etc. Or these successive events of waiting for a suggestion, verifying it, accepting it, and then waiting, verifying, accepting, which I showed in the video. And then on the other side, there's kind of these patterns that have nothing to do with Copilot, where the program is writing code, rejecting whatever suggestion shown, and then go back to writing code, and the cycle repeats. One last insight I want to present is that, as we saw in the video, a lot of the suggestions are verified after you accept them. So on average, for a lot of these suggestions where the programmer is deferring their verification, they only spend on average 3 seconds, in that verification state before accepting. But after they accept, they might spend an average of 22%, 22 seconds verifying that suggestions. And so when we account for that post-verification time, we see a 5-time increase in average verification time of suggestions. So we really need to properly account for verification times and acceptance rate. And so really here, our main takeaway is that we can understand interaction by building this taxonomy of human states. And really, it allows us to diagnose the interaction and identify inefficiencies that future work can remedy. And we have 3 design and metric suggestions for builders of these autocomplete and Copilot systems. The first one is understanding as a metric the time spent on these cop states and how it's evolving with updates to the model. As an interface suggestion, we commonly see that if you know the user's current cop states, you can better serve their needs. So if you know the user is waiting for a suggestion, maybe you want to speed up inference time for that particular user. Or if you see them prompt crafting, maybe you want to wait for them to finish their prompt before showing them a suggestion. And third, we really need to adjust verification time and acceptance rates to account for what happens after accepting a suggestion. Thank you so much for listening, and you can look at our paper online as well as code and data for the study.